Welcome to another deep dive.
Always exciting.
Today we're going to be exploring the human heart and circulatory system.
Yeah.
And you've provided us with a pretty interesting mix of sources here. Textbook excerpts, medical definitions, some real-world application examples.
Yeah, it's going to be cool to tie it all together.
It is.
Yeah.
I always love it when we get this kind of blend of sources. Gives us like a multi-dimensional perspective.
Absolutely.
And for our listeners, I hope you're ready to have your minds blown because this system is truly remarkable.
Yeah. You know, it's one of those things, like, we take it for granted, right?
Cool.
The heart just keeps on beating
Yeah.
year after year.
Yeah.
But when we really delve into the complexity, oh my goodness.
It's mind-boggling.
It is. It's mind-boggling.
So let's dive right in.
Let's do it.
One of the first things that jumped out at me, and I have to admit, this is something I kind of had a misconception about, was the heart's location. I always kind of pictured it, smack dab in the middle of the chest.
Yeah, right in the center.
But apparently it's not that simple.
It's a little more nuanced than that.
It is.
Yeah.
So where is it really?
So it's located in an area called the mediastinum.
Mediastinum.
Yeah.
Okay.
And it's actually tilted about 2/3 to the left.
Wow. 2/3 to the left.
Yeah, so not quite center stage, as we might imagine.
That's so interesting.
It is.
I never knew that.
And that leftward tilt actually, comes into play when, like, doctors are doing procedures.
Oh, really?
Like if they need to access the heart for surgery or, like, insert a catheter. That leftward tilt is a key landmark.
It's like a map almost.
It is. It's like a roadmap for them.
Okay, so even just basic positioning is really important.
Absolutely.
For medical reasons.
Yeah.
Fascinating.
It is, yeah.
Now, here's something else that kind of blew my mind. The size and shape of the heart are not fixed.
No.
They're influenced by a lot of factors.
They are. Things like age, fitness level, even disease can affect its size and shape.
That's amazing. It's almost like...
It's like a living sculpture.
Yeah.
Constantly being molded by our choices, our lifestyle.
Like a marathon runner, for instance, would they have a different heart shape?
Absolutely. You know, a marathon runner's heart might be significantly larger and more powerful.
Really?
Than someone who leads a more sedentary life.
Just because of the demands.
Exactly. It's the body's remarkable ability to adapt to the demands we place on it.
Okay, so the heart's not just this static organ. It's actually...
It's a dynamic organ.
Yeah, dynamic.
Ever-changing.
It's changing throughout our lives, responding to what we do.
Yeah.
That's pretty awesome. Now let's talk about the pericardium.
Okay, the pericardium, it's like a double-walled sac.
Double-walled sac.
That surrounds the heart, and it plays a super important role in protecting it.
Okay, so protection.
It's essential for protection.
So what does it actually do? Like, how does it protect the heart?
Think of it as a combination of, like, a seatbelt and a lubricant.
Interesting.
Okay, the outer layer is tough and fibrous. It anchors the heart in place.
Okay, so that makes sense.
And prevents it from overstretching.
Oh, okay. Like a seatbelt.
Right, exactly.
Keeps it in place.
Yeah.
And then you said lubricant, so there's something else going on there.
There is. The inner layer actually has two parts with a fluid-filled cavity between them.
Fluid-filled cavity.
Yeah. So that fluid acts as a lubricant.
Oh.
Allowing the heart to beat millions of times.
Wow.
Throughout our lifetime. Right.
Yeah.
Millions and millions of times without those surfaces rubbing against each other.
Okay, I see.
And wearing out. You know, imagine.
So it's like
if you were trying to move your fist back and forth inside a balloon filled with water.
Oh, that's a good analogy.
Yeah, that's kind of what's happening with the heart.
So it's like a shock absorber, too.
It is. It's like a shock absorber and lubrication system.
Amazing.
Built right in.
Okay, so we've got this perfectly positioned, well-protected heart.
Yeah.
But what's going on inside?
So inside we have 4 chambers.
Okay.
2 atria and 2 ventricles.
Atria and ventricles. I remember those from, like, high school biology.
Right. They're the basic chambers of the heart.
Okay, remind me, what do they each do?
So think of the atria as the receiving chambers.
Receiving chambers.
Yeah. They have these little ear-like pouches called auricles.
Auricles. Okay.
Which help to increase their capacity for holding blood.
Okay, so they're like the entryway.
They are. They're like the entryway to the heart.
And the ventricles are the...
The ventricles are the powerhouses.
Powerhouses. They're pumping.
The pumping chambers.
Yeah.
Exactly. And the walls of the ventricles are much thicker than the atria because they need to generate...
More force.
They need that force to propel blood throughout the body.
Makes sense. So it's like Receiving and then pumping.
Receiving and pumping, that's the basic action.
Okay, so it's a two-step process.
Mm-hmm.
Now, I remember something about the heart having different sides.
It does. Each side has its own separate circuit.
Oh, that's right. The right side and the left side.
Yep, the right side handles deoxygenated blood.
So that's the blood coming back from the body.
Exactly, returning from the body.
And the left side.
The left side is all about that freshly oxygenated blood coming from the lungs.
Okay, so it's like two coordinated systems.
It is. Two sides working in perfect sync.
Fascinating. But how does all this blood actually move through the heart? I mean, we've got chambers, we've got different sides. What keeps it all flowing in the right direction?
That's where the valves come in.
The valves?
They're like the gatekeepers of the heart.
Gatekeepers. Okay, so they make sure.
They make sure the blood flows in one direction.
Okay.
And prevent backflow.
So like one-way doors?
Exactly. One-way doors for the blood.
Now, I remember reading about all these different types of valves. Tricuspid, bicuspid, pulmonary, aortic. It gets a little confusing.
Yeah, it can be a bit overwhelming at first. Let's break it down.
Okay.
So we've got 4 valves in total.
Okay.
2 of them are called atrioventricular valves.
Atrioventricular, meaning?
Meaning they're located between the atria and the ventricles.
Okay, so between the receiving chambers and the pumping chambers.
Precisely. On the right side, we have the tricuspid valve.
Tricuspid.
And on the left, we have the bicuspid valve, also known as the mitral valve.
Okay, so those are the AV valves. What about those other 2?
We've got the pulmonary valve, which guards the exit from the right ventricle to the lungs.
So that's where the deoxygenated blood goes out.
That's right, on its way to get oxygenated.
And then?
And then we have the aortic valve.
Aortic.
This one controls the flow from the left ventricle to the aorta.
So out to the body.
Out to the body. The aorta is the body's largest artery. It's the main highway for oxygenated blood.
Okay, so we've got the chambers, we've got the valves, and we've got this basic flow of blood. But how does it actually travel through the body? What are the actual pathways?
So there are 2 main circuits that we need to talk about.
2 main circuits.
The pulmonary circulation and the systemic circulation.
Pulmonary and systemic. Let's start with pulmonary. What's that all about?
Think of pulmonary circulation as like a quick trip to the lungs for a refresh.
The refresh. I like that.
Deoxygenated blood.
Mm-hmm.
It enters the right atrium.
Okay.
Flows through the tricuspid valve into the right ventricle.
Right ventricle.
Mm-hmm. And then it gets pumped through the pulmonary valve into the pulmonary artery, which carries it to the lungs for a fresh supply of oxygen.
So that's the pulmonary loop.
That's the pulmonary loop. Short and sweet.
Short and sweet.
Yeah.
Now, what about systemic?
Systemic circulation, that's the grand tour.
Grand tour.
This is where that oxygen-rich blood gets delivered to every nook and cranny of the body.
Okay, so starting
from the lungs, that oxygenated blood flows through the pulmonary veins.
Pulmonary veins.
Back to the heart, into the left atrium.
Left atrium.
Then it passes through the bicuspid valve into the left ventricle and gets pumped out through that aortic valve into the aorta.
Right, and the aorta we said was like the main highway.
Main highway, exactly.
And so from there...
From there, it branches off into smaller and smaller arteries, eventually reaching the capillaries.
Capillaries.
Yeah, those are the tiny blood vessels where the actual exchange happens.
So like a delivery system.
It is. It's like a complex delivery system.
Amazing.
Ensuring every cell in our body gets what it needs.
Okay, so that's how the blood gets to all the different parts of the body. But what about the heart itself?
Ah, good question.
It needs oxygen and nutrients, too.
It does. The heart has its own dedicated network.
Really?
Yeah, it's called the coronary circulation.
Coronary circulation.
It's a network of arteries and veins that supply the heart muscle itself.
So like a mini circulatory system just for the heart.
Exactly. It's like its own personal fuel line. The main arteries branching off the aorta right at the beginning are the left and right coronary arteries.
Okay, and those are the ones that
can cause serious trouble if they get blocked.
Right, because that's a heart attack, isn't it?
That's a heart attack, yeah.
Yeah.
It's a major problem.
So those are critical.
Critical for keeping the heart running smoothly.
Okay, so we've talked about the heart as a pump, but what actually powers those contractions?
That's where cardiac muscle comes in.
Cardiac muscle.
It's a specialized type of muscle tissue.
How is it specialized?
It's striated, kind of like the skeletal muscles we use to move our limbs.
Okay.
But it's also involuntary, meaning we don't have to think about making our heart beat.
That's a good thing.
It is a good thing. Imagine having to remember to tell your heart to beat every second of every day.
I don't even want to think about it.
Right.
That would be way too much work.
Yeah, it would be exhausting. But what's even more remarkable is that these cardiac muscle cells
Okay.
They're connected by special junctions that allow them to communicate.
Communicate.
Yeah, ensuring that they contract in a coordinated way.
It's like teamwork.
It is. It's like a perfectly synchronized team down there.
Amazing.
It is.
So we've got this muscle that's working together. It's involuntary. But what actually triggers those contractions in the first place?
Each heartbeat is initiated by an electrical signal.
Electrical signal.
Yeah. It's called an action potential.
Action potential.
And this originates in the heart's natural pacemaker.
Pacemaker?
Yes, it's called the sinoatrial node, or SA node for short.
I say node, so it's like the conductor of the heart.
Exactly. It sets the tempo for the heartbeat.
Okay, and then what happens? How does that signal spread?
So this action potential spreads rapidly through the heart, causing the muscle cells to depolarize.
Depolarize, now that's a new word. What does that mean?
It essentially means a change in electrical charge across the cell membrane. It's this electrical change that ultimately causes the heart muscle to contract.
So the electrical signal leads to a change in the cells.
Yes.
And that makes them contract.
Right. And it all happens in a fraction of a second.
So it's like a chain reaction.
It is. It's like a perfectly orchestrated chain reaction.
With the electrical signal spreading through the heart, triggering those perfectly timed contractions.
Exactly. It's an amazing system, and understanding it helps us make sense of so much about the heart.
Right, like how fast it's beating.
Yeah, the heart rate.
And any problems with the rhythm.
Exactly, rhythm problems, and even how certain medications affect the heart.
It's like the foundation for understanding how the heart works.
It is. It's the electrical language of the heart.
Wow, the electrical language of the heart. That's a great way to put it. So we've got this signal spreading, but how does it make sure all the different chambers are contracting in the right order? I imagine timing is everything here.
Timing is crucial, and that's where the cardiac conduction system comes in.
Cardiac conduction system.
Think of it as the heart's internal wiring.
Internal wiring.
It's a network of specialized fibers that transmit that electrical signal with precise timing.
So the SA node starts it.
The SA node initiates the signal.
And then?
It spreads through the atria first, causing them to contract.
Okay.
And then it reaches a really important junction called the atrioventricular node, or AV node for short.
AV node. Is that just a relay station?
It's more than just a relay station. It actually delays the signal slightly.
Delays it? Why?
This delay, it gives the ventricles time to fill with blood before they contract.
So it's all about timing.
Exactly. It's a carefully timed pause.
Makes sense.
Ensuring everything stays in sync.
And from the AV node?
From the AV node, the signal travels down a pathway called the bundle of His.
Bundle of His.
Yeah, and this bundle splits into the right and left bundle branches.
Branches.
Carrying the signal to the ventricles.
Okay, and then finally those signals reach?
The Purkinje fibers.
Purkinje fibers. And they're the ones that actually make the ventricles contract.
Precisely. They spread the electrical impulse throughout the ventricles, causing that contraction.
And the way they're arranged, is that important too?
It is. They're arranged in a way that ensures the ventricles contract from the bottom up.
Why is that important?
It efficiently squeezes the blood out of the heart.
Wow, so it's not just about the signal?
It's about the direction, too.
The direction, the timing.
It's all choreographed.
That's incredible.
And all of this happens in a fraction of a second, over and over again, without us even having to think about it.
It's a beautiful system.
It is a beautiful system, but any disruption, any disruption in that finely tuned electrical system can lead to an irregular heartbeat.
This is an arrhythmia.
That's right. An arrhythmia.
And those could be?
They can range from harmless to life-threatening.
Yeah, so this electrical system is not just fascinating, it's crucial for our health.
Absolutely. It's vital.
So we've got this electrical activity, this incredible conduction system, but there must be a pattern to the actual heartbeat cycle, right? Like a clear sequence of events.
There is. We call this the cardiac cycle, and it's a beautifully synchronized sequence that repeats with every single heartbeat.
Okay. So what are the main phases of this cardiac cycle?
It all starts with a period of relaxation.
Relaxation.
We call it diastole.
Diastole. So the heart is just chilling out.
It is. The heart chambers are relaxed, and blood is passively flowing from the atria into the ventricles.
Okay, so it's like a refilling phase, getting ready for the next contraction.
Precisely. Then comes systole.
Systole.
The contraction phase. First, the atria contract, giving that final push to fill the ventricles completely.
Right, so it's like squeezing that last bit of toothpaste out of the tube.
Exactly.
Okay, and then
the ventricles contract.
The main event.
The main event, yeah.
Sending blood out to the body.
Right. The right ventricle pumps blood to the lungs, and the left ventricle, the more powerful of the two, pumps blood out to the rest of the body.
Okay, so we've got diastole, the relaxation,
right,
atrial systole, and then ventricular systole.
And then the cycle repeats.
And repeat. It's like a perfectly choreographed dance.
It is a dance of the heart.
Ensuring that blood flows in the right direction at the right time.
Precisely.
But how much blood are we talking about here? Like, how much is the heart actually pumping out with each beat?
That's where cardiac output comes in.
Cardiac output. Okay, what is that exactly?
Cardiac output is simply the volume of blood pumped by each ventricle per minute.
Per minute, okay.
It's a measure of the heart's efficiency.
Efficiency, makes sense.
And it's calculated by multiplying the stroke volume by the heart rate.
Stroke volume, that's how much blood is pumped with each beat, right?
You got it.
Okay, so a higher heart rate or a larger stroke volume would both lead to a higher cardiac output.
Exactly. It's like a simple multiplication problem.
Right. I mean, what about our resting cardiac output? Like, how much is our heart pumping when we're just relaxing?
At rest, the average cardiac output is about 5 liters per minute.
5 liters. That means our entire blood volume is circulating through our heart every minute.
That's right.
Wow.
It's pretty impressive.
It is. But we know the heart can pump way more than that during exercise, right?
Absolutely. And that difference between resting and maximum cardiac output is called cardiac reserve.
Cardiac reserve. So that's like our heart's hidden power.
Exactly. It reflects the heart's ability to adapt to those increased demands.
That's amazing.
It is. It's like having a superpower that we can tap into when we need it.
I like that. Now, what actually determines how much blood is pumped with each beat? That stroke volume. I saw some interesting terms in our sources. Preload, contractility, and afterload.
Yes. Those are the key factors that regulate stroke volume.
Let's break those down. What is preload?
Preload refers to the degree of stretch on the heart muscle fibers just before they contract.
See how stretched out they are.
Exactly. Think of it like stretching a rubber band. The more you stretch it, the more forcefully it snaps back.
Okay, that makes sense. So greater preload means a more powerful contraction.
Precisely. And this relationship is actually described by something called the Frank-Starling law of the heart.
Frank-Starling law? What's that all about?
It states that the more the heart muscle is stretched during diastole, the stronger the subsequent contraction will be.
Okay, so the heart is kind of like a self-regulating pump.
In a way, yes. The more blood it receives, the harder it contracts to pump it out.
That's pretty cool. What about contractility?
Contractility refers to the forcefulness of the heart's contraction, independent of preload. It's like the heart's inherent strength.
So even if the preload is the same, the heart can contract more forcefully if its contractility is higher.
Exactly. And contractility is influenced by various factors, including the availability of calcium ions, which are essential for muscle contraction. Things like calcium levels in the blood can actually affect how strongly the heart contracts.
That's pretty amazing.
It is.
So we've got preload, contractility. What about that last one, afterload? What does that mean?
Afterload is the pressure that the ventricles need to overcome to push blood out of the heart.
Okay.
And it's mainly determined by the pressure in the arteries.
So if our blood pressure is high, that means the afterload is high, and the heart has to work harder to push the blood out.
Exactly. And a higher afterload can actually reduce the stroke volume because the heart has to work harder just to overcome that pressure.
So it's like a balancing act.
It is a balancing act.
The heart's constantly adjusting its output based on these 3 factors.
Preload, contractility, and afterload.
To make sure everything is flowing smoothly.
That's right. It's a remarkable system of feedback and adaptation.
It's amazing. Now, we've been focusing on the heart itself, but what about all those blood vessels that carry the blood throughout the body?
Yes, the blood vessels, the highways and byways of our circulatory system.
They're essential for transporting blood to every corner of our body. Let's dive into that world.
Let's do it. We've got arteries, arterioles, capillaries, venules, and veins. It's quite the network.
It's a whole world in there. And each type of vessel has its own unique structure and function.
Absolutely.
Perfectly designed for its role.
Perfectly designed.
Let's start with arteries. Those are the thick-walled vessels that carry blood away from the heart.
That's right. They need to be strong and resilient.
Strong, okay?
Because they're dealing with that high pressure generated by the heart's contractions.
Right. It's like a powerful force pushing the blood out.
Exactly. And they have a thick layer of smooth muscle.
Full muscle, okay.
That allows them to expand and contract.
So they can adjust the blood flow.
Precisely. They're regulating blood flow. Think of them like the major highways of our circulatory system.
Highways. Built for high traffic.
Exactly.
Now, what about arterioles? Those are smaller, right?
They are. Arterioles are like the off-ramps.
Off-ramps.
Leading to the smaller roads.
Okay.
They branch off from the arteries,
Right.
and they play a crucial role in controlling blood pressure and distributing blood flow to specific tissues.
So they're like the traffic directors.
In a way, yes. They help direct blood flow to where it's needed most.
Okay, and then capillaries. Those are the tiniest blood vessels.
The tiniest, yeah. They form a vast network that reaches every single cell in the body.
Every cell. That's amazing.
It is. And capillaries are where the real action happens. This is where the exchange of oxygen, nutrients, and waste products takes place.
So that's where the blood actually delivers the goods and picks up the trash.
Exactly. It's like the delivery and waste removal service of the body.
And their walls are super thin. All right.
Incredibly thin. Just a single layer of cells, which allows for efficient diffusion.
Diffusion. That's where substances move from an area of high concentration to an area of low concentration, right?
You got it.
Okay, so it's like a natural flow.
It is. It's all about concentration gradients.
So the oxygen and nutrients move from the blood into the tissues.
Right.
And waste products move from the tissues into the blood.
Precisely. It's a constant exchange happening at the capillary level.
Wow, it's amazing how such tiny vessels play such a vital role.
It is remarkable.
But once that exchange happens, the blood needs to get back to the heart.
It does.
That's where the venules and veins come in.
Right. So if arteries are the highways carrying blood away from the heart, veins are the return routes bringing it back.
Back to the heart. Okay.
They have thinner walls than arteries and often have valves to prevent backflow.
Valves to keep the blood flowing in the right direction.
Exactly. And they rely on a couple of things to help propel that blood back to the heart.
What kind of things?
Skeletal muscle contractions.
Oh, so like when we move our legs. That helps push the blood back up.
It does. It helps squeeze the veins. And also changes in pressure during breathing.
Oh, wow. So even just breathing is helping our circulation.
It is. It's all connected.
It's incredible. So it's this whole system of pumps and valves
working together
to overcome gravity and get that blood back to where it needs to be. Now let's dive a little deeper into that exchange process that happens at the capillaries. It's called capillary exchange, right?
That's right. Capillary exchange. It's essential for maintaining life.
Okay, break it down for me. How does it actually work?
Well, we've already talked about diffusion.
Mm-hmm.
That's where substances move from areas of high concentration to low concentration.
Right. That's how oxygen and nutrients get into the tissues and waste products get out.
Mm-hmm.
But is there anything else going on?
There's also something called transcytosis.
Transcytosis, what's that?
It's a more complex process involving tiny vesicles.
Vesicles.
Yeah, they're like little transport pods that carry larger molecules across the capillary wall.
So it's like a special delivery service for those bigger molecules.
Exactly. It's like a cellular packaging and delivery service.
Pretty cool. And what about bulk flow? I saw that term in our sources too.
Bulk flow is the movement of fluid driven by pressure gradients.
Pressure gradients.
Yeah.
So it's like the force of the blood pushing things along.
Exactly. It's a dynamic process that helps regulate the fluid balance between the blood and the tissues.
Okay, so we've got diffusion,
right,
transcytosis,
right,
and bulk flow.
All working together
to orchestrate this incredible exchange of substances at the capillary level. It's amazing.
It is. When you think about how many capillaries there are in the body, the sheer volume of exchange happening every second is mind-boggling.
It's like a bustling marketplace at the microscopic level.
It is. A constant flow of goods and services.
Now let's zoom out a bit and talk about blood pressure and blood flow throughout the entire circulatory system. What are some of the factors that influence these crucial variables?
Well, blood pressure is the force that blood exerts against the walls of the blood vessels.
Okay, blood pressure. It's essential for driving blood flow, right?
Exactly. Got to have that pressure to keep things moving.
So what factors affect blood pressure?
Well, there are a few key players. Cardiac output.
Right, that's how much blood the heart's pumping out each minute.
Exactly. And then blood volume.
Which is affected by things like how much fluid we drink.
Fluid intake, urine output, that kind of thing. And then vascular resistance.
Vascular resistance. Now that's a new one. What's that?
Vascular resistance is the opposition to blood flow within the vessels.
Opposition. So like how much the vessels are pushing back against the blood.
Yeah, you could think of it that way.
So if the heart's pumping harder, or we have more blood volume, or if our blood vessels are constricted, all those things would increase blood pressure.
You got it. They all contribute.
Makes sense.
Yeah.
Now, what about vascular resistance? What determines that?
Vascular resistance is mainly determined by the diameter of the blood vessels.
Okay, so the size of the pipes, basically.
Exactly. Wider pipes, less resistance.
Right.
Then there's blood viscosity.
Viscosity, that's like the thickness of the blood, right?
Right. Thicker blood, more resistance.
Makes sense.
And then the total length of the blood vessels also plays a role. Longer vessels, more resistance. So it's a combination of those factors.
Okay, so it's like a complex equation.
It is. A lot of variables go into it.
Now, what about blood velocity? Is that the same as blood flow?
Not exactly. Blood velocity is the speed at which blood is traveling through the vessels. Blood flow is the volume passing a certain point over time.
So velocity is about speed and flow is about volume.
Precisely.
Okay. And where is blood velocity the highest?
It's actually highest in the aorta.
The aorta.
Yeah.
Because it's the biggest vessel.
Exactly. And it gradually slows down as the blood reaches those smaller arterioles and capillaries.
Why does it slow down?
Mainly because the total cross-sectional area of the blood vessels increases as they branch out.
Oh, so it's like a river flowing into a delta.
Perfect analogy. As the river widens, the water flow slows down.
So even though the blood's flowing slower through those capillaries, it actually helps with that exchange process, right?
Exactly.
Yeah.
It gives more time for substances to move between the blood and the tissues.
It's like slowing down to enjoy the scenery.
I like that.
So we've talked about blood flowing out to the body, but how does it all get back to the heart? Especially from the lower extremities, where gravity seems like it would be working against it.
That's a great question. It seems like an uphill battle, literally.
Right, defying gravity.
But the body's got a couple of tricks up its sleeve.
Oh!
The skeletal muscle pump and the respiratory pump.
Skeletal muscle pump and respiratory pump. Okay, what's the skeletal muscle pump?
Think about what happens when you move your legs. Those contractions, they actually squeeze the veins.
Oh, so just walking around?
Yep. Helps push blood back towards the heart.
That's amazing. And to prevent backflow, I'm guessing those valves in the veins play a role.
Absolutely. The valves act like one-way doors, ensuring blood flows in the right direction.
So it's a system of pumps and valves all working together to defy gravity.
Exactly. It's teamwork at its finest.
What about the respiratory pump? How does breathing help get blood back to the heart?
The respiratory pump, it utilizes the changes in pressure in the chest during breathing.
Okay.
When you inhale, the diaphragm moves down, and that creates a lower pressure in the chest, which helps draw blood upwards.
So even when we're just sitting still, our breathing is contributing to blood flow.
It's a subtle but important factor, definitely. It all adds up.
It's amazing how our bodies use these simple actions to help our circulation.
It is. It highlights the interconnectedness of all those systems in the body.
Now, we've talked about blood pressure, blood flow, venous return, but how does our body actually control and regulate all these processes? There must be some kind of control center, right?
You're right, there is. It's located in the medulla oblongata.
The medulla oblongata, that's part of the brainstem.
That's right. And this control center, it's called the cardiovascular center.
Cardiovascular center.
It's like mission control for the circulatory system.
Okay, and how does it know what adjustments to make?
It receives input from sensory receptors located all over the body.
Sensory receptors. So they're like little spies sending information back to headquarters.
Exactly. They provide information about blood pressure, blood chemistry, even physical activity.
So the cardiovascular center is getting all this information, and then it sends out signals.
It does. It sends signals to the heart and blood vessels.
Telling them what to do.
Exactly. It's constantly making adjustments.
To keep things balanced.
To keep that circulatory system running smoothly, it adjusts heart rate, contractility, vascular resistance, all to maintain that optimal blood pressure and flow.
Okay, so it's a master conductor.
It is. It's orchestrating the whole symphony.
Now, what are these sensory receptors that are sending all this information?
We've got proprioceptors.
The proprioceptors, those sound familiar.
You might remember them from our episode on the musculoskeletal system.
Oh, right. They're the ones in our muscles and joints that sense our body position and movement.
Exactly. They tell the cardiovascular center how active we are.
Okay, makes sense.
What else?
We've got baroreceptors.
Baroreceptors.
These are pressure sensors.
Pressure sensors.
Yeah. They're located in the walls of the major arteries, keeping tabs on blood pressure. So they're like the blood pressure monitors.
Exactly. They're constantly sending updates to the cardiovascular center, letting it know if the pressure is too high or too low.
Okay, so those are important for regulation.
Absolutely crucial.
Yeah.
And then we've got chemoreceptors.
Chemoreceptors.
These guys are sensitive to changes in blood chemistry.
Blood chemistry.
Things like oxygen levels, carbon dioxide, and pH.
So they're monitoring the chemical composition of the blood.
Exactly. They make sure everything stays within a healthy range.
It's amazing how our bodies are constantly monitoring all these different things.
It is. It's all about maintaining that delicate balance.
So we've got the nervous system controlling things through that cardiovascular center.
Right.
But there are also hormones involved in regulating blood pressure and blood flow, right?
You got it. Hormones play a crucial role as well.
Okay, tell me more about that. Which hormones are we talking about?
Well, one key player is antidiuretic hormone, or ADH.
ADH. That rings a bell. Helps us conserve water, right?
Exactly. It helps the kidneys reabsorb water, which increases blood volume.
And more blood volume means more pressure.
Exactly. So ADH is all about preventing dehydration and maintaining that blood pressure.
Okay, so it's like our body's water conservation specialist.
I like that. Then we've got epinephrine and norepinephrine.
Oh, those are the fight or flight hormones, right?
The very same. They increase heart rate, contractility, and vascular resistance.
So they're like the emergency responders of the circulatory system.
Exactly. They kick in when we need a sudden boost.
Like when we're exercising.
Or when we're facing a stressful situation.
Okay, so they're all about increasing blood flow when we need it most. Are there any other hormones involved?
There are a few others. Aldosterone, for example, helps regulate sodium and water balance, which also affects blood volume and pressure. And then there's angiotensin second, a potent vasoconstrictor.
It's like a team effort.
It is. All these hormones working together.
To fine-tune our circulatory system.
That's right. It's a complex interplay, but it's remarkably effective.
It is. Now, it's not just the brain and hormones that are involved in regulating blood flow, right? Our tissues also play a role.
You're thinking about autoregulation.
Autoregulation, yes. That's where the tissues themselves can adjust their own blood flow based on their need.
Precisely. It's a local control mechanism.
So how does that work?
There are two main types of autoregulation.
Okay.
Metabolic autoregulation and myogenic autoregulation.
Okay, let's break those down. What's metabolic autoregulation?
Metabolic autoregulation, it's driven by changes in the chemical environment within the tissues.
So what's happening there?
Well, imagine a muscle that's working hard.
Okay.
It's going to consume more oxygen.
Makes sense. It needs more fuel.
Exactly. And it's going to produce more carbon dioxide and other metabolic byproducts.
Okay, and those byproducts, they're the key.
They are. Those metabolic byproducts act as local vasodilators.
Vasodilators, meaning?
Meaning they cause the blood vessels to relax and widen, which increases blood flow to that area.
So the tissue is essentially signaling its need for more blood.
Exactly. It's like saying, hey, I'm working hard here, send more supplies.
Okay, that's pretty cool. What about myogenic autoregulation?
Myogenic autoregulation, that's a response to changes in pressure within the arterioles themselves.
So if blood pressure increases.
If blood pressure increases, the smooth muscle in the arterial wall stretches.
Okay.
And that stretching triggers a reflex contraction.
A contraction, so it squeezes the vessel.
Exactly. It constricts the arteriole, which reduces blood flow.
Oh, so it's like a protective mechanism.
Exactly. It prevents excessive blood flow to the tissue when pressure is high.
Makes sense. And if blood pressure drops?
Then the arteriole relaxes, allowing more blood to flow through.
So it's like a self-adjusting valve.
You could think of it that way, yeah.
Amazing.
Right.
It's like this system of checks and balances.
It is constantly adjusting.
Ensuring that blood flow is regulated at both the systemic level
Right.
and at the local level.
Exactly. It's a remarkable example of the body's ability to maintain homeostasis.
It really is. It's like this beautifully orchestrated system that keeps everything in balance.
It is. Now, we've been focusing on the control mechanisms, but let's not forget about the specific routes that blood takes as it circulates throughout the body. It's like exploring the intricate roadmap of our circulatory system.
Right. We talked about the systemic and pulmonary circuits, but there are so many branches and pathways within those. It's like a network of highways and back roads.
Exactly. It's all about getting blood to where it needs to go, and just like any good road trip, we need a starting point. Our starting point is the heart, that central pump that sends blood out through those two main circuits.
Right. The systemic circulation for the body and the pulmonary circulation for the lungs.
Precisely. And within the systemic circulation, there are numerous branches and pathways, each supplying blood to specific regions and organs. Think of it like a delivery system with different routes for different destinations.
Okay, can you give us some examples of those major arteries that carry blood away from the heart?
Sure. One of the first major branches off the aorta is the brachiocephalic trunk.
Brachiocephalic trunk. Okay, what does that supply?
It further divides into the right common carotid artery and the right subclavian artery.
Right common carotid and right subclavian. So those are going to the right side of the head, neck, and arm.
Exactly.
What about the left side?
The left common carotid and left subclavian arteries branch directly off the aorta. They're responsible for supplying blood to the left side of the head, neck, and arm.
Okay, so we've got blood flowing to the brain and arms.
Yeah.
What about the rest of the body? How does it get its blood?
As the aorta descends through the chest, it gives rise to branches like the coronary arteries. Those are the heart's own blood supply. And then it branches off into the celiac trunk.
Celiac trunk. What does that supply?
The celiac trunk provides blood to important organs in the abdomen, like the stomach, liver, spleen, and pancreas.
Okay, so those are getting their share of that oxygen-rich blood.
Exactly. And then as the aorta continues down through the abdomen, it branches off into other major arteries, like the superior mesenteric artery for the small intestines, the renal arteries for the kidneys, and so on.
The kidneys are super important for filtering waste products, so it makes sense they have their own dedicated blood supply. Are there any other major branches we should know about?
Further down, we have the gonadal arteries, which supply the reproductive organs, and the inferior mesenteric artery, which provides blood to the lower parts of the intestines.
Wow, it's like a carefully planned network ensuring every part of the body gets what it needs.
It is. And eventually, as the aorta reaches the pelvis, it splits into the two common iliac arteries.
Those are for the legs and pelvis, right?
Exactly. And from those iliac arteries, smaller branches arise, eventually leading to those arterioles and capillaries where the exchange takes place.
So we followed the arteries, that outward journey of blood.
Right, but we can't forget about the return trip.
The venous system. How does all that blood get back at the heart after making its deliveries?
Well, just like we have major arteries, we have major veins to carry blood back to the heart.
Okay, give me some examples.
Blood from the head and neck is drained by the jugular veins.
Jugular veins.
They empty into the subclavian veins.
Okay.
And blood from the arms is drained by veins like the cephalic vein, the basilic vein, and the median cubital vein.
The median cubital vein. Isn't that the one they usually use for drawing blood?
You got it.
The one that makes everyone nervous.
That's the one. But all those veins, they eventually drain into those subclavian veins too.
Okay, so everything from the head, neck, and arms is going into the subclavian veins. What happens next?
The subclavian veins, they join with the internal jugular veins to form the brachiocephalic veins.
Brachiocephalic veins, so one on each side.
Exactly. And then those two brachiocephalic veins merge to form the superior vena cava.
The superior vena cava.
The large vein that returns blood from the upper body to the right atrium of the heart.
Okay, so that takes care of the upper body.
Right.
What about the blood coming back from the lower body?
Blood from the legs and pelvis is drained by the iliac veins, which merge to form the inferior vena cava.
Inferior vena cava.
The largest vein in the body.
Wow, the largest.
And that one also empties into the right atrium, completing the loop.
So we have two major veins, the superior vena cava and the inferior vena cava.
Right.
Bringing all that blood back to the heart.
It's a beautifully designed system, very efficient.
It really is. Now, earlier we talked about how the body can adapt blood flow to meet different demands, like exercise.
Yes, exercise. That's when the circulatory system really kicks into high gear.
Right. It has to adjust to keep those muscles supplied with oxygen.
Exactly. One of the most noticeable changes during exercise is an increase in heart rate.
Right. Our heart starts beating faster.
It does. As our muscles work harder, they need more oxygen.
Makes sense.
And that triggers an increase in both heart rate and stroke volume.
Stroke volume, that's the amount of blood pumped with each beat, right?
Exactly. So the heart is pumping faster.
Okay.
And it's pumping more blood with each beat.
Which means more blood is getting to the muscles.
Exactly. But the changes don't stop there.
What else happens?
Blood flow actually gets redirected during exercise.
Redirected meaning?
Blood flow to the working muscles increases, while blood flow to less essential organs, like the digestive system, decreases.
So it's all about prioritizing.
Exactly. It's like diverting traffic during rush hour.
Makes sense. But how does the body actually do that?
It's a combination of neural and hormonal mechanisms.
Okay, so the nervous system and hormones are both involved.
Right. The sympathetic nervous system, remember our fight or flight response?
Yeah, that kicks in during exercise too.
It does. It causes vasoconstriction in the arterioles supplying those non-essential organs.
So it's like closing down some of those roads.
Exactly. And at the same time, it promotes vasodilation in the arterioles supplying the working muscles.
Opening up the floodgates.
Exactly. So the blood is diverted to where it's needed most.
And those fight or flight hormones, epinephrine and norepinephrine, they're involved in this too.
They are. They contribute to both the increased heart rate and that vasoconstriction.
Okay, so they're like the traffic controllers directing blood flow.
A great analogy.
It's fascinating how this all works together so seamlessly.
It is. And don't forget about the local factors within those muscles.
Oh, right. You mentioned those earlier.
As muscles work harder, they produce metabolic byproducts.
Things like carbon dioxide and lactic acid.
Exactly. And those act as local
So
vasodilators.
the muscles are signaling their own need for more blood,
Exactly. They're saying, hey, we need more supplies down here.
and the body responds.
It does. The circulatory system is constantly adapting to meet those changing demands. It's a remarkable system.
It really is. Now, with all this knowledge about how the heart works, its structure, its pumping action, its electrical system, and its ability to adapt, what stands out to you as the most remarkable aspect?
You know, what always gets me is that the heart beats continuously for a lifetime, day in and day out, without any conscious effort on our part.
It's easy to take that for granted.
It is. It's a testament to the autonomy and resilience of this organ.
It's like it has a mind of its own.
In a way, it does. And the fact that it generates its own electrical impulses.
Right, it's like a self-powered machine.
Exactly.
Yep.
And when you consider how it adjusts its output based on those factors we talked about, preload, contractility, and afterload, it's clear that this is a remarkably sophisticated system.
It's truly an engineering marvel.
It is. And the network of blood vessels delivering blood to every corner of our body, it's equally impressive.
Right, it's like a vast and intricate highway system.
With different types of vessels, each perfectly designed for its role.
And it's all orchestrated by that cardiovascular center in our brain, constantly monitoring and adjusting things to meet our needs.
Right. And let's not forget about the body's ability to respond to those challenges like shock.
Oh yeah, those compensatory mechanisms are incredible, redirecting blood flow to those vital organs.
It's a testament to the body's resilience, its ability to adapt and survive.
It's truly amazing. Now, as we've been going through all this, what's one thing that really surprised you, something you didn't know before?
You know, I was really struck by learning about the pericardium in more detail.
The pericardium, that fluid-filled sac around the heart.
Yes, I knew it was there, but I never fully appreciated its role in reducing friction and allowing the heart to beat smoothly without wearing out.
Right, it's like the heart's own personal lubrication system.
Exactly. It's a brilliant design feature.
So simple, yet so effective. Now, for our listeners who've been with us on this journey, exploring the depths of the cardiovascular system, what's one key takeaway you'd like them to remember?
I think the most important takeaway is that the heart is not just this static pump. It's dynamic, it's adaptable, it's constantly responding to the body's needs. It's working tirelessly to keep us alive.
That's a beautiful way to put it.
Yeah.
Now, as we wrap up this second part of our deep dive, I want to leave our listeners with a thought-provoking question. Given everything we've learned about the heart's incredible adaptability, what are some ways you can personally support its health and function throughout your life?
That's a great question to ponder. And as you consider that, I encourage you to explore the connection between your lifestyle choices, things like diet, exercise, stress management, sleep, and your cardiovascular health. The choices we make every day, they have a big impact on our hearts.
Wise words.
Thank you.
Well, it looks like we've reached the end of part 2 of our deep dive. We've covered a lot of ground today,
We have.
but there's always more to explore, right?
Yeah.
So stay tuned for part 3, where we'll dive into some more intriguing details and insights about this incredible system that keeps us going. Welcome back to part 3 of our deep dive into the amazing world of the human heart and the circulatory system. We've already uncovered so much, from the heart's anatomy to those incredible blood vessels that carry blood throughout the body.
It's like we've been on an incredible journey exploring this hidden universe inside of us.
It really is. And in this final part of our deep dive, we're going to explore some of the things that can actually go wrong with this intricate system.
Right, because even the most well-designed systems can sometimes have hiccups.
Exactly. Our sources mention heart murmurs, which are those whooshing sounds that doctors sometimes hear when they're listening to the heart.
Yeah, those are interesting.
What exactly causes those?
Heart murmurs, they're caused by turbulent blood flow.
Turbulent blood flow.
And that's often due to a valve that isn't closing properly.
Oh.
So it's like a leaky faucet.
Leaky faucet. So some of the blood is...
Some blood leaks back through the valve, yeah, creating that whooshing sound.
So it's like a backflow?
It is. It's a backflow of blood.
Interesting. And are all heart murmurs bad?
Not necessarily. Some heart murmurs are actually harmless. They don't cause any problems, but others...
Can be a sign of something more serious.
Exactly. So it's always a good idea to have any unusual heart sounds checked out by a doctor just to be safe.
Always better to be safe than sorry, especially when it comes to our hearts.
Absolutely.
And we've talked about those electrical signals that control the heartbeat.
Right. Those are essential.
But what happens when those signals get disrupted? That's when we run into those arrhythmias, right?
Exactly. Arrhythmias, They're basically irregularities in the heart's rhythm.
Irregularities, okay. So the heart's not beating in that nice, steady pattern.
Right. And they can be as simple as a skipped beat, like a little flutter,
Okay.
or as serious as a life-threatening condition.
Wow, that's a pretty wide range. What actually causes those arrhythmias?
Well, they can be caused by problems with the heart's electrical conduction system. Remember that SA node, the heart's natural pacemaker?
Yeah, that's the one that sets the rhythm.
Exactly. So if that malfunctions, or if there's a blockage in one of those conduction pathways, that can throw off the whole rhythm.
So it's like a short circuit in the heart's wiring.
That's a good analogy.
And are there any other things that can trigger them?
Oh, yeah, for sure. Things like stress, caffeine, certain medications, even electrolyte imbalances can sometimes trigger an arrhythmia.
Wow, so a lot of things can affect it. So that racing heart you get after one too many cups of coffee.
That could actually be an arrhythmia.
Oh, wow. So how do we know if it's something to be concerned about?
Well, many arrhythmias are benign, meaning they're not harmful.
Okay.
But some can disrupt the heart's ability to pump effectively.
Right, that's a problem.
Exactly. So if you experience any unusual heart rhythms, especially if you're also having symptoms like dizziness, shortness of breath, or chest pain, it's always best to get it checked out by a doctor.
Right. Those are definitely red flags.
They are. Those are signs that something might be wrong.
Now, we can't forget about coronary artery disease. It's one of the leading causes of death worldwide, and our sources go into quite a bit of detail about it.
It's a very serious condition.
What causes coronary artery disease, and how does it actually affect the heart?
Coronary artery disease, or CAD, is a condition where plaque builds up inside the coronary arteries.
Plaque.
It's like the sticky stuff made up of cholesterol and other fatty deposits.
And the coronary arteries, those are the ones that supply blood to the heart muscle itself, right?
Exactly.
So if those get clogged up, that's a big problem.
It is. It's like clogging the heart's fuel lines.
Okay, and so what happens as that plaque builds up?
It narrows the arteries, reducing blood flow to the heart muscle.
Okay.
And that can lead to chest pain, which is called angina.
Angina.
I've heard of that. Especially during exertion, when the heart needs more oxygen.
So like when we're exercising.
Exactly. The heart's working harder, but it's not getting enough blood.
Okay, and if one of those arteries gets completely blocked, that's when we have a heart attack.
That's right. A heart attack, or myocardial infarction, happens when a coronary artery is completely blocked, cutting off blood supply to a portion of the heart muscle. And without that blood supply, the heart muscle can be damaged or even die.
So it's like a major traffic jam.
It is.
In one of the heart's main supply routes.
Exactly. And that can have devastating consequences.
It's a reminder of how important it is to take care of our hearts.
Absolutely. Prevention is key when it comes to heart health.
Now, as we wrap up this incredible journey through the heart and circulatory system, what's one final thought-provoking question you'd like to leave our listeners with? Something to ponder as they go about their day.
I think it's important to remember that the heart is more than just an organ. It's a symbol of life, strength, and resilience. It works tirelessly behind the scenes, keeping us going. So let's take a moment to appreciate this incredible gift.
I love that. To appreciate our hearts.
Yes, and let's make choices that support its health and well-being.
Well said. Well, that brings our deep dive into the amazing world of the human heart and circulatory system to a close.
It's been quite a journey.
It has. A huge thank you to you for joining us on this exploration.
Thank you for having me. It's been a pleasure.
We'll be back soon with another deep dive into a new topic, so stay tuned. Until then, keep those hearts pumping strong, those minds curious, and remember to take good care of yourselves.